All right, let's talk about spin. I mean, really talk about it. From the wheels on your car to planets hurtling through space, there's a whole branch of physics dedicated to how things rotate. And today, we're going to break it all down.
So think about this. If something's moving in a straight line, it's super easy to describe, right? You just talk about its distance, its speed. Simple. But what about a spinning wheel? Every single point on that wheel is moving, some faster than others. But the wheel itself isn't really going anywhere. So how on earth do we even begin to describe that motion?
Okay, to get our heads around this, we basically need to understand that motion comes in two main flavors. You've got your straight line or linear motion, and then you've got your spinning in a circle or rotational motion. And what we're going to do today is learn how to connect those two worlds.
Linear motion is, exactly what it sounds like. A car driving down a straight road. That's linear. It's just getting from point A to point B. But rotational motion? That's the wheels of that same car, spinning around and around a central point.
So, how do we build a bridge between these two different kinds of motion? Well, it turns out we need a special kind of tool. It's a whole new way of looking at angles, and it's called the radian.
Now, I know what you're thinking. Angles? We use degrees for that, right? 360 degrees in a circle. We learned that in school. And you're right. But for some reason, physicists tend to ignore degrees. So what's the deal? Why do they do that? Is there something wrong with degrees?
The answer, of course, is the radian. See, the number 360 for degrees is kind of random, just a number someone picked a long time ago. But the radian is built right into the geometry of the circle. Picture this. You take the radius of a circle, that's the distance from the center to the edge. Now imagine you could pick up that line and literally wrap it around the outside edge. The angle that piece of arc makes back at the center, that is 1 radian.
And because the radian has the radius literally baked into its definition, it becomes the natural way to measure angles in physics. It creates this beautiful, direct link between the spinning angular world and the straight line linear world of distance. It's the secret key that unlocks everything.
Okay, so now that we've got our secret key, the radian, we can start talking about the main players in rotational motion. And the cool part is, you're going to see that they all have a twin in the linear world, which should make them feel surprisingly familiar.
Just take a look. For every linear idea, there's a rotational one right next to it. So where we have x for linear distance or displacement, in the rotational world, we use the Greek letter theta. For linear velocity v, we have omega. And for linear acceleration a, we have alpha. So let's quickly run through what these mean. Angular displacement, theta, is just how far something is turned. And, you guessed it, we measure it in radians. Angular velocity, omega, is how fast it's spinning. So that's going to be radians per second. And finally, angular acceleration, alpha, tells us if that spin is speeding up or slowing down.
All right, we have our concepts for both worlds. We have our special tool, the radian. Now for the magic part, let's see how they all connect with a couple of really elegant formulas.
First up is something called arc length, which we'll just call S. And the formula is just S equals r theta. So what does that mean? It means the actual linear distance a point travels along the edge of a circle is just its radius, r, multiplied by the angle it spun through, theta. And because we're using radians, the math is just that simple. It's incredibly clean. And guess what? We can do the exact same thing for speed. The actual straight line speed of a point on a spinning wheel, we call that its tangential velocity, v, has a very similar formula. It's just v equals r omega. So the linear speed is the radius, r, times the angular speed, omega.
Here's a great way to think about it. Picture a vinyl record spinning on a turntable. Every single spot on that record is spinning at the same angular speed, right? It all goes around once in the same amount of time. But a tiny speck of dust on the outer edge has to travel a huge circle compared to a speck of dust right near the center label. Since it has a bigger radius, that outer speck has to be moving way, way faster in a straight line sense just to keep up. That's v equals r omega playing out right in front of you. So we've kind of learned this new language of rotation and seen how it ties back to the motion we're all used to. But so what? Let's take a step back and talk about why this actually matters. Because when you understand this stuff, when you can speak rotation, you suddenly unlock the secrets to how a huge chunk of our universe works.
We're talking about everything from the majestic spin of entire galaxies and planets, all the way down to the nitty-gritty mechanics of a car engine, or even how a figure skater can pull their arms in to spin impossibly fast. It's all the same fundamental physics. So, we've seen how the radiant is this amazing bridge that connects the two worlds of motion, and let's just describe how things spin. Now, think back to linear motion for a sec. We all know that a force is what makes something speed up, right? A push or a pull causes acceleration, which leads to a really interesting question. What's the rotational version of a force? What's the push or pull that makes something start spinning in the first place? Well, that's a story for another time. Thanks for joining me.